So this video will look at finding some trig function values for theta, and the double angle will also come into some of the examples. So we'll start off with looking at an angle in between 0 and pi over 2. So 0, 90 degrees, that means we're here in first quadrant, right? 0 to 90, first quadrant, everything's positive. So it should be not too bad with calculation. So we've got the sine of theta is 8 over 11. So we're not really interested in what theta is. Theta is something between 0 and pi over 2. But from that sine ratio, I would like to be able to find things like cosecant, tangent, cosine, and then apply those to the sine of 2 theta and the cosine of 2 theta. Okay? So whenever we did these before and we looked at the sine and we wanted all the other trig functions, if we restrict ourselves to quadrant 1 and make an angle, regardless, arbitrary point, doesn't have to be exact, from the origin, there's our point, here's our theta, we could create a right triangle in which we know the sine ratio, which in a right triangle is opposite over hypotenuse, and we can label our right triangle in our figure for the side opposite theta is 8 and the hypotenuse is 11. And we can use Pythagorean theorem, a squared plus b squared equals c squared, to find the missing leg in this figure. So we have 8 squared plus b squared equals 11 squared, so 64, and this is 121. We subtract those, we get 57. So b ends up being the square root of 57. It's plus or minus, but we're in quadrant 1, so we'll keep this as just the square root of 57, which is like 7 something, decimal wise, 7.5, a little over. So it's a leg, it should be smaller than 11, so numerically we're good to go. So now that we have that other side, we could find cosecant. Wouldn't actually be that hard to find, because cosecant is simply the reciprocal of sine, which we already have. So cosecant would just be 11 over 8, or hypotenuse over adjacent in this right triangle figure. Okay, so then tangent of theta is going to end up being, using the ratio opposite over adjacent, because that's the tangent ratio in a right triangle, and now that we're using theta from the origin here, we can do 8 over square root of 57 for our tangent ratio. Cosine ratio is adjacent over hypotenuse, so we can make that square root of 57 over 11. And square root of 57 doesn't simplify. So, I mean, you could pull cotangent, you could pull secant, the other two trig functions, but those are sufficient for now. Want to address finding sine of 2 theta and cosine of 2 theta. So, if I look at finding the sine of 2 theta, again, I don't have to know what theta is, and I don't have to double it, and I don't have to think about it being a horizontal compression by a half or anything like that. I have a formula for the sine of 2 theta that says it's the same as 2 times the sine of theta times the cosine of theta. And we have those. We have that the sine of theta is 8 over 11, and we also have that the cosine of theta was square root of 57 over 11. So we can simply plug those in to this double angle formula for sine and do 2 times 8 over 11 times square root of 57 over 11. And it's not a very pretty fraction, but it ends up being 16 square root of 57 over 11, not 11, 121. 11 times 11, we're not adding, over 121 as the exact answer for sine of 2 theta. Okay. When we do cosine of 2 theta, there were a few ways you could write that. There's 2 cosine squared, 1 minus sine squared, cosine squared minus sine squared. You have sine and cosine, so really it's up to you what you would like to use, because it should get you the same answer. So I'm going to do, I think I'll use the one with sine squared. 1 minus 2 sine squared theta, which is like 1 minus 2, and then you take sine theta and square it. So we have that again. we have that sine theta was 8 over 11. So I'm simply going to replace 1 minus 2 times 8 over 11 squared. And then follow order of operations, I need to square the 8 over 11 first. So that's 64 over 121. Then I'll multiply that by 2. It's like 2 over 1. So I get 1 minus 128 over 121. And then in doing that, when I subtract, 1 minus, like 121 over 121 minus 128, I get negative 7 over 121. Now, we can talk about that in that when we did this to begin with, and we did theta, when our sine value was 8 over 11, I mean, this is the answer. But when we did our sine value before, the angle was about 46 degrees. I know we didn't have to find it, but just doing sine inverse of 8 over 11, just as like a little side note here, sine inverse of 8 over 11 gave an angle of about 46.7 degrees. And if I were to double that, the angle itself, I would get 93.3 degrees. So I would expect the cosine for that angle to be negative because now it's in quadrant 2. The sine value is positive, being in quadrant 2 when it got doubled, but the cosine value is negative. But that's finding the double angle values with the single angles that we found using Pythagorean theorem. Okay. Here's another one. Sine of theta is 3/5. Theta is now in quadrant 2. So that's going to affect cosine values. We have the sine values. Sine values go with y coordinates, the vertical, which are positive, so that's fine. But we want to find sine of 2 theta, cosine of 2 theta, and tangent of 2 theta. So envision, second quadrant over here, and you have your angle. Again, the angles always come as reference angles from the x-axis. If we created our right triangle, our sine ratio puts opposite of 3 with a hypotenuse of 5. And this ends up being a 3, 4, 5 Pythagorean triple triangle. If you do Pythagorean theorem, you'll find that the other leg is 4. But because we're in quadrant 2, and because we're going out on the horizontal left, we're going to have to make that a -4 because of where it's positioned in quadrant 2. So when we go and do the cosine of the angle, it's -4/5 instead of positive, because again, the cosine value in quadrant 2 needs to be negative, so that's going to make it -4/5. So now, if I want to find the sine of 2 theta, there's a formula, substitution replacement identity that we can use for that says I can multiply 2 times the sine of theta times cosine of theta, for which I have values now. And I can just simply plug those in. So that gives me 2 times 3/5 times -4/5, and multiplying those fractions straight across is going to give us -24 over 25 for the value of sine of 2 theta. Okay? Cosine of 2 theta, that one has 3 options. They all use the sine or the cosine, so it really wouldn't matter which one you use. I think I'll use the one that does 2 cosine squared theta minus 1. Again, the other two you most certainly could have used because all 3 of them use a single, use a sine or a cosine, either single or squared. Actually, they all use squared, either sine or cosine squared, which we have. So in using that, and again, remember, cosine squared theta is like cosine of theta that gets squared. So I'm just going to plug in the -4/5 here. So 2 times -4/5 quantity squared minus 1. You have got to remember order of operations and apply this square first, making that 16 over 25. Then we'll multiply the 2 like it's 2 over 1. So we get 32 over 25. And then we'll subtract 1. And that is like subtracting 25 over 25 if you had a common denominator. and that turns into 7 over 25 for the cosine of 2 theta. Now, for the tangent of 2 theta, there is a tangent identity formula that says the tangent of 2 theta is 2 times the tangent of theta over 1 minus tangent squared of theta, which we didn't find, but tangent is -3/4. However, again, you can plug that in here if you want to, but you could also express the tangent ratio of 2 theta as the sine of 2 theta over cosine of 2 theta, because that's by definition what tangent is, sine over cosine, and we have values for those. So we could make -24 over 25 divided by 7 over 25. We're dividing fractions, so instead of writing it vertically, I'm going to write it out horizontally and put divide by 7 over 25, which is going to multiply 25 over 7 to -24 over 25. My 25s will cancel, and I'll get that the sine of 2 theta is -24 over 7. Again, you could have went through this tangent of 2 theta identity using the fact that tangent of theta based on our initial drawing opposite over adjacent is 3 over -4. You most certainly could have done that, plugging it in for all the tangent theta squaring, but you could also get the same thing by using the sine over cosine ratio. So given sine theta, we have found exactly the sine, cosine, and tangent of 2 theta. Okay? All right. Here's one that goes in the other direction. So say you're given the cosine of 2 theta is 2 over 7, and you're in the first quadrant, which is always helpful, and it wants you to find the cosine of theta. You cannot simply half everything because you half the angle back. You can't just half the number. So the fact that we're given cosine of 2 theta is 2/7, we actually have a representation for cosine of 2 theta in 3 different formats that will help us find the cosine of theta. I'm going to replace it with, again, there's 3 options here. I don't want to replace it with anything that has sine because I'm trying to find cosine. So if I replace cosine of 2 theta with its identity 2 cosine squared theta minus 1, I can now solve for cosine. Okay, so I'll add 1 to both sides and get 2 cosine squared equals, so adding 1 would be like adding 7 over 7, so that would be 9 over 7. Then I'll divide both sides by 2, or multiply by 1/2, if that's easier on your visual. Cosine squared ends up being 9 over 14. And now, because I have a function squared and I want to solve for it, I'll just square root both sides. So cosine would be plus or minus 9 over 14. Because we're only in quadrant 1, I'm only interested in the positive. And if I split the square roots, square root of 9 is 3, and the square root of 14 would just stay square root of 14. If you want to leave that in the denominator for now, you can. And that's exactly what the cosine of theta would be, 3 divided by the square root of 14. All right, so this sort of goes in an opposite direction and uses one of the identities for the double angle, or the formula for the double angle. But because we were finding cosine, I picked the one that just had a cosine in it to make that the most useful process.